Okay, this is our AP Physics homework set, UT Quest on work and energy. Some of you might have got to this problem and I don't know, might have started crying, might have started going to Google, might have started texting your friends. This is actually a really good problem. It blends a lot of our physics concepts together in one problem. Okay, let's take a look how we solve this. This is a very, very multi-step problem, and I'm going to go through the steps that you're going to need to do. Not only do you need to go on through the steps, but on this one here, it's one of those rare problems that's actually better solved backwards. In other words, let me look at my final state and work backwards to my initial state. And this is kind of an uncomfortable thing to do, but it works extremely well for this problem. All right, so this is what we're given, and ultimately we're trying to find out this delta x. How far was the spring compressed? Well, the big idea here is we're going to use conservation of energy. If I know the amount of energy that the object left the spring, like for instance, if I knew the amount of energy right here, I could easily calculate the spring energy. Unfortunately, from here, I lose a little bit of energy due to the work done by friction. And then I'm here, and then I gain some potential energy before I get to here. All right, our first challenge is to find this velocity, which is not a bad thing because that's going to give us our energy at this point. And then if I can get the energy at that point, then I can set it equal to the spring energy here, and then I've solved the rest of the problem. Okay, so to get this velocity right here, first of all, we're going to treat this as a kinematics problem. All right, so I have a half parabola projectile motion. I know this, so I can go to kinematics equations, and I can go to this equation right here. I know since this is a half parabola horizontal launch, this V initial is 0. This allows me to compute time. All right, we did that in our projectile motion unit. Now, once I've got this time, I can use it in this equation. I know the distance in the x, and I can calculate this velocity. I call this point C. I just need to break this up into different points. All right, so the velocity at point C is now known. Okay, that's one of my answers that I can enter. What's really important is if I know the velocity here at this point, I can calculate the kinetic energy. Now from here to here, there's no change in potential energy. It's level. All right, but there is a difference in the energy here to here because of this little sticky spot with friction. So friction is going to do some work. So as I go from here to here, I'm going to lose energy due to that work of friction. Let's find out how much energy I'm going to lose right there. Okay, before I do that, here's my energy at point C. I just computed this. I know the mass. So I can compute my energy at this point right here. Now this energy is lower than the energy here because we have work lost due to this friction. Now how do I do that? Well, I know that energy lost is the same thing as work. So my energy lost from B to C is going to be equal to the amount of work done by friction. Okay, well, what's the work done by friction? Well, it's a friction force acting over a certain distance. I call it a negative. Why? I'm displacing this way. The force of friction is acting that way. So this work will be negative. And that makes sense. I will lose energy from here to here. All right, so how do I get the force of friction? Well, that's mu k, force normal. Force normal is going to have an equal magnitude to the weight. So I know all of these variables, so I can calculate that work done by friction. Okay, now here we need to think about this a little bit. My energy at point C plus the work lost to friction equals the energy at point B. All right, but I thought you said the work was negative and the energy was lost. It is, but remember, we're going backwards. So if I lost energy this way, then I want to add that energy back because ultimately I want to find the energy here at B. Okay? So the energy at B is the energy at C plus this energy lost on this sticky spot, right? So this is going to give me my energy at B. Now once I have my energy at B, that's going to be easy. That's just going to be equal to the energy of the compressed spring. And I think we're given this. We found this by taking our energy at C, adding the lost work to it. So we have the energy total, and the energy total at B has to be equal to the energy total at A. All right, so I'm able to compute this K. All right, and then it asks, okay, what is my velocity right here? Well, there's an easy way and there's a hard way. I know the velocity here. I know my kinematics. And remember that V final is a vector sum of Vx added to Vy. And then I can get this result through Pythagorean. If you want to go through that pain, knock yourself out. But let me show you an easier way. All right, so let's get the velocity final. Well, if I look at my scenario, by conservation of energy, my energy at point C and my energy here have to be equal. Well, what I'm going to do is I'm going to now call this my zero potential energy reference level. So that means at this point here I've got some kinetic energy due to this velocity, and I have some potential energy due to this height. When I get to here, it's all kinetic energy, and potential energy becomes zero. All right, energy at C, we already found that. And I have to add some potential energy to it, and that's going to be equal to my final energy, which is all kinetic. And the potential energy here has gone to zero. So all we need to compute is V final. And we've got that problem.